This is a classic example of dynamic programming where this approach is used to derive a solution for this puzzle. The Tower of Hanoi or Towers of Hanoi is a mathematical game or puzzle. It consists of 3 rods and a number of disks of different sizes which can slide onto any rod. The puzzle starts with the disks in a neat stack in ascending order of size on one rod, the smallest at the top, thus making a conical shape. The objective of the puzzle is to move the entire stack to another rod, obeying the following rules. Only one disk may be moved at a time. Each move consists of taking the upper disk from one of the rods and sliding it onto another rod on top of other disks that may already be present on that rod. No disk may be placed on top of a smaller disk. The dynamic programming solution consists of solving the functional equation as shown below, where n denotes the number of disks to be moved, h denotes the home rod, t denotes the target rod, not parentheses ht denotes the third rod, neither h nor t. The semicolon denotes concatenation, and s parentheses n h t equals solution to a problem consists of n number of disks that are to be moved from rod h to rod t. Further, observing the dynamic programming solution for the puzzle, note that for n equals 1, the problem is trivial, namely s within parentheses 1, h, t equals to move a disk from rod h to rod t. There is only one disk left. The number of moves required by this solution, therefore, is 2 to the power of n minus 1. If the objective is to maximize the number of moves without cycling, then the dynamic programming functional equation is slightly more complicated, and 3 to the power of n minus 1 moves are required. When the recursions proceed from the last stage toward the first stage, this approach is called backward dynamic programming. Clearly, by symmetry, we could also have worked from the first stage toward the last stage. Such recursions are called forward dynamic programming. In general, one can adopt either one of these two approaches to solve a problem. There is, however, a difference in the byproducts produced by these two methods. In solving a problem by backward dynamic programming, we will obtain as byproducts the optimal values from every state in every stage to the end, whereas in solving a problem by forward dynamic programming, the corresponding byproducts would be values from the initial states in the first stage to every state in the remaining stages. Now, a closer look of the areas of application of dynamic programming. The Needleman-Wunsch algorithm. The Needleman-Wunsch algorithm performs a global alignment on two sequences called A and B here. It is commonly used in bioinformatics to align protein or nucleotide sequences. The algorithm was published in 1970 by Saul B. Needleman and Christian D. Wunsch. The Needleman-Wunsch algorithm is an example of dynamic programming and was the first application of dynamic programming to biological sequence comparison. It is sometimes referred to as the optimal matching algorithm. Dynamic time warping (DTW) is an algorithm for measuring similarity between two sequences which may vary in time or speed. For instance, similarities in walking patterns could be detected even if in one video the person was walking slowly and if in another he or she were walking more quickly, or even if there were accelerations and decelerations during the course of one observation. Dynamic time warping has been applied to video, audio, and graphics. Indeed, any data which can be turned into a linear representation can be analyzed with dynamic time warping. A well-known application has been automatic speech recognition to cope with different speaking speeds. In general, dynamic time warping is a method that allows a computer to find an optimal match between two sequences, example time series, with certain restrictions. The sequences are warped non-linearly in the time dimension to determine a measure of their similarity independent of certain nonlinear variations in the time dimension. Debor's algorithm. In the mathematical subfield of numerical analysis, the Debor algorithm is a fast and numerically stable algorithm for evaluating spline curves in B-spline form. Next, the statistical mechanical lattice models for protein DNA binding in chromatin. Statistical mechanical lattice models for protein DNA binding are well established as a method to describe complex ligand binding equilibria measured in vitro with purified DNA and protein components. Recently, a new field of applications has opened up for this approach since it has become possible to experimentally quantify genome-wide protein occupancies in relation to the DNA sequence. This method uses dynamic programming approach. Neurodynamic programming or reinforcement learning, which is the term used in the artificial intelligence literature, uses neural network and other approximation architectures to overcome such bottlenecks to the applicability of dynamic programming. A dynamic programming approach for newborns incubator humidity control. The rate of evaporative heat exchange between the skin surface of a very premature infant and the surrounding incubator air may be so high that evaporative heat loss alone may exceed the infant's total metabolic heat production. However, it has been demonstrated in several investigations published in recent years that basal evaporative water loss can be consistently reduced by increasing the ambient humidity. Nevertheless, the passive humidification system, or the water reservoir, used in most incubators cannot achieve high and steady humidity levels. Here, the authors propose an active humidification system. The algorithm is based on a combination of optimal control theory and dynamic programming approach. A look at more algorithms that use dynamic programming. Backward induction as a solution method for finite horizon discrete time dynamic optimization problems. Next, method of undetermined coefficients can be used to solve the Bellman equation in infinite horizon discrete time discounted time invariant dynamic optimization problems. Also, many string algorithms, including longest common subsequence, longest increasing subsequence, longest common substring, Levenshtein distance. Moreover, many algorithmic problems on graphs can be solved efficiently for graphs of bounded tree width or bounded click width by using dynamic programming on a tree decomposition of the graph. Next, the Koch-Younger-Casamy (CYK) algorithm, which determines whether and how a given string can be generated by a given context-free grammar. Furthermore, the use of transposition tables and refutation tables in computer chess. Next, the Viterbi algorithm used for hidden Markov models. More, the early algorithm, a type of chart parser. Next, Floyd's all-pairs shortest path algorithm. Also, optimizing the order for chain matrix multiplication. Next, pseudo-polynomial time algorithms for the subset sum and knapsack and partition problems. Moreover, the Selinger, also known as System R algorithm for relational database query optimization, and recurrent solutions to lattice models for protein DNA building, and the Duckworth-Lewis method for resolving the problem when games of cricket are interrupted. The aim of this video was to offer you a concise and comprehensible account of dynamic programming, its history, the basic approach, and areas of application. We hope the video accomplished offering you what we intended. The end.